Hey everyone, we're Group 8. Our project is a simulation of swarms of unmanned ground vehicles. I'm Carter Nichols. I'm electrical engineering.
Chase Gallo, electrical engineering.
I'm Charles LaFleur, electrical engineering.
I'm Jesselyn McDonald, computer science.
I'm Jefferson Charles. I'm a computer engineer.
So this is the outline for what we are going to go over in this presentation. We are first going to start with the purpose and the goals of the project. Then we will discuss project requirements and constraints. After that, it will be the purpose of the ROS2 framework and the ROS2 Swarm package. Then it would be the design of the implementation of the project. Then it would be project testing and results. And then finally, we will go over the discussion, state of the art, and future works. So the project goals, the goal of the project is to customize and test an open source package used for the swarming of robots. This package being ROS2 Swarm. We wanted to use this package because it is decentralized. It's a decentralized robotic swarm, and this prevents a single point of failure. Basically, that's saying that if one thing fails, the entire system as a whole fails. It being decentralized should prevent this, which is what we want. We also want to implement a form of decision making to facilitate and highlight the capabilities of robot to robot communication in this decentralized network. We also want to create custom patterns to not only demonstrate how creating patterns works in this package, but to also create a pattern which allows more user controllability in the form of allowing the user to control a robot. And we will discuss more of what that pattern is.
So project requirements and constraints. So first of all, what is ROS2 and why is it needed? So ROS itself stands for the Robotic Operating System, and it's an open source framework or middleware that's used for developing, managing, and operating robotic software. And also is very useful because it provides tools and libraries and a simpler framework for creating both robust and complex applications and movements. For example, the TF2 package it provides is perfect for doing matrix transformations under the hood without the user having to worry about it or the developer having to worry about it. And so ROS2 is the second version of ROS, and it focuses on making the original ROS framework more decentralized by using a data distribution service. And there's many different kinds of data distribution services, but the one that ROS2 Foxy uses, which is the distro we're using, uses a fast RTPS. And so this removes the master node architecture while keeping the publish subscribe architecture, making it a common framework that people are used to. And it takes advantage of something called the global and local namespace hierarchy, which is also very pertinent for decentralized systems. And so the ROS to Swarm framework utilizes and builds on top of ROS2. And it takes advantage of the data distribution service and also the local and global namespace. And so ROS to Swarm is a very nice package because it minimizes the amount of data traffic going over the network, which leaves room for scalability of the robots. It does this by making sure each robot is executing its task or patterns individually. Like here in this bottom picture, you can see that robot 0 is a local namespace, and all of the nodes and topics are created inside this local namespace, meaning it's running purely on the robot and there's not too much communication going between the host computer and the robot or going between the robot and another robot, therefore minimizing the amount of data going over the network. And it also provides a custom library for matrix and vector calculations. This is different from the TF2 library I mentioned a second ago. It uses something they made called the Scan2 functions, and it has different kind of functions for creating potential fields, attraction fields, repulsion fields for object detection and avoidance. And so this here is the Turtlebot subsystem hardware for the robot that we use. It consists of a 360-degree LiDAR for both 2D mapping and obstacle avoidance. It also has a Raspberry Pi 3B model on it, which you can't see in this picture here. But that's the main processor, and that's also has a Wi-Fi module that it uses to communicate to the host computer over the network. And then has an OpenCR board, which is basically the central control unit of this Turtlebot, and it facilitates communication between the sensors and processor and motors, kind of offloading some processing power from the Raspberry Pi and also acting as the motor drivers.
Project design. So here's our overall system overview. So we have our host computer, which we use to perform simulations by using DStart simulation bash script. We also use our host computer to connect to each of the Raspberry Pis on each of the Turtlebots using a script that we created that connects to the IP of each of the robots. And then once we connect to each of the robots, we do, using the start robot bash script file, we start that, and then that initializes that movement pattern that we're gonna perform on the robots, and it initializes the LiDAR sensor that we're using also. And then once we have the that bash script running with the movement pattern, we do the start command pattern or bash script that starts the movement pattern on each of the robots. And here's our overall ROS2 Swarm subsystem. So we start with the user selecting the movement pattern, and then the LiDAR starts detecting objects around it and sends it to the drive command, or either the hardware protection layer. And inside the hardware protection layer, it detects if there's a nearby object, and if there is, it sends it to the collision avoidance. And a adjusted drive command pattern is calculated. And if there is no object near the Turtlebot, that is sent to that the movement pattern that the user selected is just executed towards the drive command, and that's sent to the motors, and then the robot performs whatever movement pattern, or if there's an object near the robot avoids that object. And then here's our Turtlebot subsystem design. The communication with the Turtlebots would be set up by our Wi-Fi network, and the antenna that is built on the Raspberry Pi in the Turtlebot will be the main line for communication. Using the ROS master node, that will be the central point of communication within the Turtlebot, and it will be the main node in which everything communicates through. The Turtlebots use a method called the publish and the subscribe method, which is where a component a component in the Turtlebot will publish data to a topic, and if another component needs data from that topic, then it will subscribe to that topic. And there may be multiple publishers or subscribers to certain topics, but none of them have any notice of their existence. And with the ROS master node would be an access point that will set up the connection between the host computer and the topics that the Turtlebots will publish to.
Project implementation. The basic movement patterns of the turtle bots are all the patterns that we make use of obstacle avoidance through the hardware protection layer. We have the drive pattern, which is the moving straight forward, ahead, or in reverse. It'll continue moving until it encounters an object, and it will adjust its course and continue moving forward or backwards. The attraction pattern is the attraction of robots to any object or robot in range. It doesn't differentiate. If it senses something, it will attract towards it. Aggregation is based off the robots aggregating around robots. This time they will determine if a robot is there by the size or height of it, and it will aggregate towards other robots. If it sees a wall, it won't do that towards the wall. Dispersion is basically the same thing, except they go in different directions away from each other at a certain determined distance. So we can make it 1 meter or 2 meters. It doesn't matter. The voting patterns are used to facilitate robot-to-robot communication. There's a node that each robot subscribes and posts to that will be a cast of their vote on what action they will do. This global namespace is published, and once a winner is decided, all votes will converge on the winner, and the robots will perform that decided action. The two different types of voting patterns are to discuss dispersion and the majority rule. Custom patterns are able to be made. We have created our own custom pattern, and we labeled it as cat and mouse. This pattern is offering more user controllability, where the user manually moves a lead robot, robot 0, and other robots will follow that robot. It will do this by checking the local namespace of each robot at startup. If the namespace reads robot 0, it will execute the TurtleBot bring up nodes rather than the ROS2 swarm bring up. This allows the user to teleop into the TurtleBot and move it with the keyboard.
Project testing. So firstly, we had our simulation testing, which involved using Gazebo, which is a application for robotics in a 3D environment. So we were able to launch our ROS2 swarm patterns on Gazebo with a specified number of robots, and we were able to successfully edit the patterns we wanted them to execute, and they were able to complete them, both movement patterns and voting patterns. We also tested some of the limitations in Gazebo, so we were able to have around a maximum of 40 robots run a attraction pattern, and they all attracted either in separate small groups or attracted all together in one big group. And this was done because we don't have 40 robots available, so we wanted to test the scalability in simulation at the very least. The discuss dispersion pattern, which is where the robots each vote on a distance to disperse to. We tested that using 5 robots, and they all voted on a distance and separated by that distance, the majority rule distance. Next, we had live testing on physical TurtleBots, and a lot of this testing involved kind of back and forth editing the YAML parameter files for the movement pattern and seeing what would change and what could be adjusted based on what we saw, because in simulation there wasn't too many obstacles. It was kind of an open area, whereas in the room, the DaVinci Lab where we had done most of our testing, there were other obstacles that could cause problems. So we had to adjust some of the parameters for the robots in order to get them to move and attract and disperse within certain ranges that we specified. Also, the cat and mouse pattern, we were able to successfully do that, but it did take a lot of trial and error. And with this pattern, we did mess around with the distance which the cat in this case would follow the mouse, and we were able to do that. These pictures show some of the dispersion patterns we did in simulation. So on the top left, there were 5 robots lined up, and then we had run the dispersion pattern, and you see they each dispersed within the distance that was specified, and then they stopped moving after. And the same thing with our physical robots, although we did not have 5 turtlebots to test this on, we did use 2, and we were able to specify a distance of 0.8 meters in this case. We measured, and they each separated by roughly 0.8 meters, but we could also change that if we desired. Some of the future works that the project has to develop is we only had 2 turtlebots, so we'd like, if we could, or another group in the future, test using more turtlebots to see how well they successfully or unsuccessfully run the dispersion attraction patterns or voting patterns and so forth, because in the physical world there's more objects that could be a problem that the turtlebots could attract to and get stuck on, so we'd have to test that. Additionally, we could continue with the clear path dingo robots, which are much larger robots, and this will likely be done based on sponsor feedback by future senior design groups. And doing this will help show that the package is Rasta Swarm is hardware independent. It could run on any robot as long as it has the proper sensors and motors, and show its scalability. And in that case with the Dingo, we'd also, like, in the future, another group would also have to use a ROS bridge likely, because Rasta Swarm is a ROS2 package, but the Dingoes run on ROS. And additionally, we would like to, or in the future groups, to implement multi-robot mapping so that we could have an area, a room we want to map, and have multiple robots on it, and they each go their own way and fill in the map and collectively complete and share that information so that we could work in parallel and have quicker mapping.